What is the most serious issue in the world?
Plastic pollution. Food waste problem.
Have you ever wondered how much plastic we produce per day?
How much food is wasted every day?
It pollutes the water we drink and the food we eat.
How many people are suffering from hunger?
However, it seems that our life cannot live without this.
Are there any better solutions for these two issues? Nothing is impossible, and here we present you our project, turning food waste into degradable bioplastic, using engineered E. coli.
Food waste has been one of the most challenging issues around the world. From research, we know that 1.3 billion of food is wasted every year, accounting for 1/3 of the total food production. Food waste has been turning into a more urgent and serious problem. In our city, Macau, about 20,000 tons of food waste is produced every year, whereas only 555 tons of them have gone through the treatment process. This shows that the rate of reduced food waste treatment is very low, down to 0.17%. The traditional and common way of treating food waste is by turning them into compost. There is another alternative solution in Macau. It's a central food waste treatment facility. The system works by producing biogas through fermentation of food waste. Then the biogases are converted into electricity. However, there's a large amount of carbon emission. Therefore, there are better solutions. Our projects hope to turning food waste into PLA and PHA. PLA, also known as polylactic acid, is an environmentally friendly bioplastic, which is biodegradable, compostable, and eco-friendly. In addition, it can be degraded without polluting the environment. On the other end, PHA is also biodegradable. The degradation products have no harmful effects on living creatures on Earth. Compared to those methods that we are using today, our solution seems to be more beneficial to environmental protection.
We did some experiments to make our system work successfully. First, to validate our plasmid as if it would be what we have expected, we have gone through the RT-qPCR to validate and analyze the gene expression of our plasmid, as shown in Fig. PHAC facing. PHA, PCT optimized and PCT gene has slight increase in expression after IPTG treatment with an increase of 0.2 to 0.6 fold change. And also, both amylase and glucoamylase after IPTG treatment have very strong expression for 80 and 480 on average respectively. Then, to know if E. coli could grow well in food waste, we simulated the environment of food waste of rice products, which is also the raw material of generating PLA. We estimated the concentration before the experiment by checking if its OD value was around OD 600. Then we transformed the green fluorescent protein gene to the E. coli to establish a model of E. coli's growth in food waste and compare the growth curve. As demonstrated by Fig 1 and Fig 2, samples with presence of food waste have also shown higher fluorescence than those without food waste. The result of our project is shown through quantitative and quantitative testing. Since the raw materials of our bioplastic production system are generated from the fermentation of monosaccharides, in our project, we would like to use amylase, breaking starch in food waste, into monosaccharides, for example glucose, to enhance the yield of bioplastic production. We have used a glucose test kit to measure the glucose concentration after the addition of our E. coli. However, the results are unreasonable in both control group and experimental group. Therefore, we plan to do further experiments to validate our construct in the future.
In addition, our team has developed a testing prototype and protocol to achieve engineering success and follow this set of protocols in the testing phase, using colony forming unit. Since the pH of the environment will have changed due to the presence of lactic acid, which can easily inhibit the growth of E. coli. And also, the results from the measurement of the food waste shown that many of the food waste from daily basis are in pH 4 to pH 7, which reduce the efficiency of the PLA and PHA production system. Therefore, in order to solve this problem, we designed an exit tolerance system comprised with FABB gene. To investigate the exit tolerance system of our engineered protein, IPTG was added to the bacterial cultures. IPTG addition was achieved at the time of 4 hours to reach the concentration of 1 millimole and incubate overnight. As demonstrated in the figure, our engineered exit-torrent system displayed a significant improvement of the E. coli growth in aquatic environment compared to their respective control. For further improvement, we hope that we can have further experiment on this and compare if it is beneficial or not to add the FABA gene in the exit-torrent system. Since we found out that exit-torrent system, which combines with FABB and FABA gene, is proven to be effective for the growth of E. coli in aquatic environment. To analyze various chemical functional groups present in the product that we have produced, we performed the IR spectrometric analysis. As shown in the figure, it can be seen that the plastic produced is not much different from the composition of the structure of the PHA and PLA respectively, and match the chemical functional groups that we expected to have. So we can confirm that these three bioplastics are what we want. In order to measure the amount of bioplastic produced, we make the nail agar plate and strike the cell culture PHA, PHAC, and PHAC facing on the plate. As shown in the figure, it can clearly indicate the mean intensity of the nail wet and shown the significant difference compared with the factor with the mean intensity of about 70. It is important to note that construct with PHAC facing had the greatest mean intensity among three constructs of about 120, which indicates that the additional of facing allowed us to promote the production of the bioplastic. Furthermore, the mean intensity of PHA and PHAC lie at 90 and 80 respectively, which illustrates a successful plastic production.
Our project goal is using E. coli to convert food waste into bioplastic. Therefore, the composition of food waste, which can largely affect the growth of E. coli, is critical. By comparing the nutrient values of the combination of food waste with LB broth, in which we assume that E. coli can grow the best, we developed a model to predict how combinations of different kinds of food waste can optimize the growth of E. coli. Besides assuming that nutrient values is the only factor that affects the growth of E. coli, we assume that sugar, protein, and fat are the major factors that affect the growth of E. coli and expect a linear correlation between nutrient value and the actual growth. We first divide the common food waste into multiple categories and obtain data of the nutrient values of every broth and different food waste from U.S. Department of Agriculture. In the prediction model, we sum up the nutrient values of different combinations of food waste and standardize it by dividing the amount of food waste. We have used root mean squared error (RMSE) to compare the nutrient values of LB broth with food waste. Then we normalize our data by defining the nutrient value of LB broth and use the calculated RMSE and relative root mean square error (RRMSE) to find the corresponding amount of each food waste needed for the optimal growth of E. coli. In order to check which is the best combination of food waste types, we average the ratio and RMSE and RMSE across the same type of food. When using the normalized RMSE prediction, the combination of rice and vegetables and the combination of vegetables and bread can best mimic the LB broth. On the other hand, the models predict that the mixture of beef and egg is the worst amount or the combinations to best mimic the environment. With regard to the unnormalized RMSE, we found some different results. For instance, the mixture of rice and bread, when combined with a ratio of 1 to 29.7, is the best combination to mimic the LB broth when predicting with the RMSE. In addition, the RMSE varies much less than the RMSE. Overall, we here use models to predict which combinations of food waste are able to mimic the LB broth and thus optimize the growth of E. coli. To best of our knowledge, this kind of food waste optimizing model has not been done in the past. Therefore, we believe this model can not only help our project, but also on other studies about food waste optimization. Moreover, our models can also apply to optimize food waste from different stock of food instead of different kinds. Due to time and resource limitations, we here did not use wet lab experiments to further check which models can generate better predictions, which is one of the things that we plan to do in the future. Also, further researchers can try to adapt non-Euclidean existence error matrix, because we would expect a linear correlation of nutrients value and the actual growth. Here, although we have not built a model that can accurately optimize using food waste for growing microorganisms, our method can provide a basis for other researchers to further their investigation.
Human practice is an indispensable part of our iGEM team by linking our project to the public. This year, our Human Practice Department has organized 7 events, including visits to like-minded organizations, holding local events, organizing an IG challenge, and interviewing stakeholders. And under the aim that we want to transfer food waste into usable products, the food waste collection part is important. So our team visited Macau Environmental Protection Bureau, in which a system has been built for manufacturing usable compost via a food waste recycling program. From the visit, we understand the details of several common food waste treatments around the world. Also, they suggest that we should try to produce our bioplastic in different pH values and different genres of food. As we know, acidic environments inhibit the growth of E. coli. To tackle the problem, we have designed the acid tolerance system, consisting of FABB gene. Results from that shows our acid tolerance system is capable for overcoming acidic conditions. And here comes next, we have made an official visit to our sponsor, the Wynn Hotel, to gain support. Our idea of turning food waste into biodegradable plastic is appreciated, and they are strongly supporting us in different sectors. In the Q&A section, the hotel questioned us about working mechanisms, comparisons with similar projects, etc. And in addition, they were concerned about the yield of bioplastic. Hence, we would like to increase the efficiency of bioplastic production, so we choose phasing, which is capable for promoting the bioplastic production rate. We will apply it to our project to improve the production of bioplastic copolymers. After starting our lab work, we soon realized that we do not have sufficient food waste samples for experiments, materials, and for the detergent workshop. So we held a food waste collecting program and contacted a local fruit shop to provide us with various food waste samples. Our team has been invited to join a global webinar organized by the University of St. Joseph, showing our project and hearing sample sharing from different experts. We have learned the classification of food loss and food waste by a German expert, Macau's food waste prevention and management analysis, the concept of food literacy, a food waste reduction initiative were shared by different stakeholders of the society, including professors, NGO members, and a waste service company manager. And we all agree that it is important to begin in small ways in our daily lives and to reduce waste at source. In order to have a wide promotion of the food waste problem, our team has organized an Instagram challenge, the Macau FW Challenge. During a 2-week time, we have received over 80 posts, and participants responded to us that it does induce them to finish all the food in their meal. To know more about biomanufacturing, we have contacted the Bluva Lab, a synthetic biology company in China. Bluva was a previous iGEM team. We are eager to know more about it, especially for commercializing and applying their project in the industrial areas and the bioplastic industry circumstances in China. Bluva thinks our project is creative for linking food waste and bioplastics, and they believe that our project can apply widely to around the world due to the high demand of food waste treatment. In addition, they shared useful statistics related to bioplastics with us. In conclusion, although we're still stuck in the COVID, but the concept of human practice has never changed. Human practice is the study of how your work affects the world and how the world affects your work. Here's the end of the human practice session.
This year, by providing a 4-month courses, our students learn about the concept of synthetic biology and some basic lab skills.
A local television company, TDM, filmed a video of us introducing the iGEM competitions and our previous projects to the public. Our team members are interviewed, also for our sponsors. And a hotel has organized a hotel tour with us while filming, in order to show how our previous project can apply into their hotel room. In September, we held a detergent workshop for primary 5 to 6 students. We separate the workshop into 3 sections. First, we made a simple introduction of iGEM and our project. Second, we taught them how to use the pineapple peels to make the handy detergent. Lastly, we taught them some simple laboratory rules and showed them some experimental device. Through this workshop, we want to let them to know that we can make good use of the food waste.
Sustainable Development Goals are a series of 17 international development goals proposed by the United Nations in 2015. In our project, we are calling action to address global environmental and social challenges, targeting 4 SDGs: Goal 2, Zero Hunger; Goal 4, Quality Education; Goal 11, Sustainable Cities and Communities; and Goal 12, Responsible Consumption and Production. To achieve these goals, collaborations with iGEM teams specifically targeting SDGs are needed. On the 18th of September, we participated in the iGEM SDG Impact Conference held by iGEM team TAS Taipei. Having discussions about ways different teams tackle the SDGs, we shared our ideas and interacted with iGEM teams around the world. Furthermore, considering the importance of stakeholders taking roles in sustainable development, we collaborated with Ms. Ruby O, the founder of the Society of Food and Environmental Health Macau, for giving a talk. Through a range of outreach activities, we are taking actions focusing on 4 SDGs, raising social awareness and collaborating through meetings. There's a large amount of people who are suffering from hunger. One of the main reasons of this is that large of food is wasted, and that the distribution of food is not balanced. Tackling the problem, we'd like to help with plastic pollution by redistributing food usage and reduce food waste generation at source. Education opportunity is one of the most important topics in our world today. To ensure inclusive and equitable quality education and promote lifelong learning opportunities for all, we're doing a lot in planning with local organizations and providing teaching materials for teaching organizations in Macau. Due to the increasingly rapid urbanization happening in Macau, it is getting more urgent and paramount to make Macau a more sustainable city. Noticing the food waste problem in Macau, we'd like to develop an alternative solution for food waste treatment, increasing food waste treatment efficiency and lowering environmental impacts. The natural environment and resources has been suffering from destructive impacts since the last few decades. Since then, we've made changes to our consumption and production patterns and are aiming for a more sustainable future. Overall, the success of the PHA and PLA production system provides a reuse opportunity for the food waste to turn into worthwhile materials. Moreover, we have our exit-tolerant gene and phase-in added to optimize the overall performance of our system. Through prediction of modeling, we can better understand which combination of food waste can best optimize the growth of E. coli. Most importantly, we successfully drew the public's attention to these 2 devastating issues through virtual events and in-person education. In the future, we hope to further boost the yield of our system in order to achieve mass production. To construct a system for the production of bioplastic from food waste, we'd also like to perform co-transformation. Furthermore, we will consider applying our bioplastic in our lives, like making plastic bags, bottles, or any other plastic products. We'd also consider building up a production line from the collection of food waste to the process of food waste and founding our bioplastic.
Here, we offer you a better solution. However, each one of us can make difference by supporting bioplastic industry and finishing all the food on your plate.
Each one of us
Can make a difference.
Can make a difference.
Together,
Together,
we make a change.